Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Back in the 1970s and 80s, my unorthodox parallel processing approach to supercomputing met a lot of resistance. I was rejected and mocked whenever I proposed that parallel processing will work. In those 2 decades, my massively parallel processing supercomputing premise was that the logic of the grand challenge problem should determine how the problem should be solved, not vice versa. That is, it's only the laws of logic and physics that are sacrosanct, not the technology that in the first place must bend for the laws of logic and physics. In an article dated June 14, 1976, the Computer World magazine interviewed the foremost supercomputer experts that were attending the National Computer Conference in New York. Those supercomputer experts unanimously told the Computer World magazine that the supercomputer theory of parallel processing will be, quote, a waste of time, unquote. In 1989, 25,000 research supercomputer scientists logged on each day onto conventional vector supercomputers. Due to that skepticism and negative press, it was widely believed that parallel processing is a huge waste of everybody's time. For that reason, I was the only person that was logged on each day onto the most powerful and the most massively parallel processing supercomputer in the world. I visualized my modern massively parallel processing supercomputer as my new internet that was powered by a global network of 64 binary thousand processors. I visualized my new internet as married together as one seamless, cohesive whole supercomputer. I visualized my new supercomputer as an ensemble of 64 binary thousand processors that were married together by 1 binary million email wires. In 1989, I was researching alone on how to use 65,536 commodity processors and how to use them to solve one grand challenge problem. In 1989, it made the news headlines that I, Philip Emeagwali, an African supercomputer scientist in the United States, has experimentally discovered how to use a new internet that's a global network of 65,536 commodity processors, and how to use that new internet to solve the toughest initial boundary value problems in calculus and physics. I experimentally discovered how to use my internet as a massively parallel processing supercomputer and use that internet to reduce the time to solution of the most computation-intensive grand challenge problems. I experimentally discovered how to speed up from 180 years or 65,536 days within only one processor to just one day across one internet. I visualize that new internet as a global network of 65,536 commodity processors. The two leading lights of sequential and vector processing supercomputing paradigms, namely Gene Amdahl and Seymour Cray, respectively, argued that it will be impossible to experimentally record the speed increase in supercomputing that I recorded in 1989. The 25,000 quote-unquote hot brains or conventional supercomputer scientists at National Science Foundation supercomputer centers stayed with conventional vector processing supercomputers. Those 25,000 supercomputer scientists stayed away from the massively parallel processing supercomputer. And the reason was that each believed that it will be impossible to use 64 binary thousand processors to solve one grand challenge problem. In contrast, I believed that it will be possible to parallel process and to do so when it seemed impossible to do so. Beyond faster computation speeds, using several cores in both computers and supercomputers has rich consequences. One such advantage of multi-core processing technology is that it increased the reliability of the modern computer and improved the fault tolerance of the massively parallel processing supercomputer. A 12-year-old writing a school report on the contributions of Philip Emeagwali to the development of the computer asked me, how do we increase the speed of quantum computers? I answered, in classical parallel computing, I experimentally discovered how to solve all 65,536 challenging problems and how to solve them at the same time, and how to solve them across a global network of 1,048,576 commodity email wires that fed data and answers from initial boundary value problems and fed them to and from 65,536 commodity processors. I discovered how to solve extreme scale problems in computational physics. My physical surroundings entered into my initial boundary value problems of a new calculus and of the fastest computational physics. I'm surrounded by the air and the water that entered into my general circulation models that I executed across my ensemble of 64 binary thousand commodity processors. I was asked, what does a quantum computer look like? I answered, the inside of a quantum computer is one of the coldest places in the known universe. The inside of a quantum computer is minus 273 degrees Celsius. The inside of a quantum computer is 150 times colder than interstellar space. The first quantum computer is not quite a quantum computer. That first quantum computer is a monolithic black box that's 12 feet by 8 feet by 10 feet tall. That first quantum computer fills a small bedroom. The quantum computer will not make the massively parallel processing supercomputer obsolete. The reason is that a quantum computer will not be a general purpose computer. The quantum computer might look like a refrigerator because it needs to be cooled. In quantum computing, the computer memory and the processor must be isolated. I experimentally discovered how to reduce the time to solution from 180 years or 65,536 days within one processor to only 1 day of time to solution across a new internet that's powered by a global network of 65,536 processors. Those processors were used to solve all 65,536 challenging problems and solve them at the same time. I began sequential processing supercomputing in the summer of 1974, and I began by wanting to discover the massively parallel processing supercomputer in 1974. I began parallel processing supercomputing without being able to visualize the modern supercomputer and visualize it in 1974. I began modern supercomputing without being able to even articulate the modern supercomputer, and to do so back in 1974. In the 1970s, my grand challenge was to visualize the shape of my internet and to visualize it as a 7,980 mile diameter internet, and most importantly, articulate that internet as the source of the fastest computations, both present and future. But back in 1974, or even in the late 1970s, I wasn't sure how my experimental discovery of massively parallel processing will be contextualized with calculus, algebra, arithmetic, codes, and emails. The reason the speed up of 64 binary thousand that I experimentally discovered made the news headlines in 1989 was that the new knowledge that parallel processing works could not be proven wrong. Like any scientific discovery, my experimental discovery was 100% doubt-free. That experimental discovery was the end product of an acid test type experiment that I conducted across a new internet that's a global network of 65,536 processors. The supercomputer that is 64 binary thousand times faster than the computer is immensely more complex than the computer.
Insightful and brilliant lecture.